Good evening, everyone. I am Mouli, and on behalf of the JBNSTS and JBSPDF family, I welcome one and all present to the very first event of the Young Scholars Exposure Initiative. This initiative was basically launched with the idea of providing our young scholars, who are basically undergraduates and postgraduates, right up to early career professionals, with a friendly platform to acquire a very important skill, or rather even brush up the much needed skill of confidently presenting to their research work to a scientific community, a skill I'm sure that is going to come handy throughout their academic and professional career. So without further ado, let's get started. It is with immense pleasure that I introduce to you our reviewers on the panel for today's event. First up, we have Dr. Debmalya Panigrahi, who is a JBNSTS scholar from the year 2000. Dr. Panigrahi is an associate professor of computer science at Duke University. He obtained his bachelor's and master's degrees in computer science and engineering at Jadavpur University, Kolkata in 2004, and IISER Bangalore in 2006, respectively. In 2012, he obtained his Ph.D. in theoretical computer science at MIT. He was a postdoctoral researcher in the theory group at Microsoft Research Redmond before joining Duke in the year 2013. Our second reviewer of the day is Dr. Sulalit Bandyopadhyay. He is a JBNSTS scholar of 2006. Dr. Bandyopadhyay earned his PhD in chemical engineering and is currently employed as an associate professor within particle engineering and hydrometallurgy at NTNU Norway. He is also employed as a researcher at the Department of Water Management, TU Delft, Netherlands. He is currently a member of the operative group for the Gemini Center within Hydrometallurgy, HYPROS. I welcome you both and thank you graciously for taking time out of your busy schedules to be a part of this event. Such support is extremely encouraging to all of us. Now, before I introduce the first speaker of the day, I ask the speakers, reviewers, and the audience to take note of a few things. The total time allotted for the talk is going to be 20 minutes. We will then take some audience questions before we move on to the valuable opinion of our reviewers. We request the audience to post any query that they have in the chat box. After that, we will move on to the reviewers. So we have two speakers today. Our first speaker of the evening and of the YSE event is Mr. Arkadeep Mitra. Arkadeep is currently an undergraduate student at the Indian Institute of Science, Education and Research, Kolkata. His interests are in abstract mathematics, theoretical physics, and biophysics. He is pursuing a BS-MS integrated course and wants to major in physics. He is a JBNSTS junior scholar from the year 2017. He is also a KVPY fellow and a NIUS physics student at HBCSE TIFR. The title of Arkadeep's talk today is Computational Quantum Mechanics, Light at the End of the Tunnel. Arkadeep, you can unmute yourself and start presenting.
Okay, thank you, Mouli, for the very kind introduction. I'll share my screen now.
Yeah, sure.
Okay. Is it visible?
Yes, Arkadeep.
Okay, thank you. I welcome all of you to this talk on computational quantum mechanics with a bit of a promising subtitle, Light at the End of the Tunnel. We begin with a short introduction on quantum mechanics, and we immediately ask the question, what is quantum mechanics? Quantum mechanics is a fundamental physical theory that describes the behavior of nature at very small scales. But you must have already known that, right? So what's new here? We ask the more pertinent question, what does quantum mechanics actually do? And we try to understand this with a very popular analogy. Imagine a ball of mass m that is constrained to move along the x-axis under the influence of a force that we know, okay? Now, classically, given the position of the ball as a function of time, which we may represent by small x here, we can find all sort of information about the kinetics of the ball. For example, you can differentiate it with respect to time to get velocity. D square x by dt square is your acceleration. You can find its kinetic energy, momentum, and so on. But how do we find the small x? We use Newton's second law, right? We use this very simple looking ordinary differential equation, and we solve this ordinary differential equation to get the position of the ball as a function of time. Note that this theory is deterministic. It tells you exactly what the outcomes will be. Quantum mechanics, on the other hand, is a probabilistic theory. It tells you what the outcomes may be with certain probabilities assigned to them, okay? And what we basically do is that we try to look for something that we call the wave function and represent by psi, and we try to solve that using the Schrödinger's equation, okay? Here, V is the potential energy distribution, H bar is Planck's constant by 2 pi. But if all of this intimidates you, let's keep this in the background for a while and understand that this is basically a differential equation with some special properties that have been highlighted in red, okay? But we still haven't answered what is psi? What's such a big deal about it? And why are we so interested in solving for psi, okay? If you ask a physicist this question, you'll get an immediate answer that psi is an abstract quantity that we call the wave function. But as soon as you hear that, you should ask the question that using quantum mechanics, we want to be able to explain observations that we can very well perceive. But an abstract quantity, on the other hand, is something that we cannot perceive by definition, right? So what does an abstract quantity have to do with our perception of the universe? The answer to this is provided by something that we call the zeroth postulate of quantum mechanics. And it is sort of a basic starting premise in the model. And I consider this to be the most important and at the same time the most underrated of all postulates in quantum mechanics. I'll read this out for you. It says that the state of a quantum mechanical system is completely defined by the wave function. And this contains probabilistic information about all physical observables. So not only does this have a sense of physical reality imbibed in itself, it has a sense of complete physical reality imbibed in itself, because any physical observable that you might be interested in, there is probabilistic information about that embedded in this abstract quantity, okay? Something to note before we go forward is that the most general case is that psi is a function of all the three Cartesian coordinates and time. And in that case, the most general form of the Schrödinger's equation is what you see here indicated by the curved arrow. But if we assume that psi is a function of one of the Cartesian coordinates and time, just for the sake of simplicity, we get the one-dimensional Schrödinger's equation, which is the one that we had been looking at for so long, and we'll be doing so throughout this talk, okay? And with that, we sort of enter into the main part of our present or our task at hand. You use this differential equation to solve for psi, okay? But what makes it seem like it may be unsolvable? The issue is much more general and pertains to all differential equations. Now, all of us at some point of our lives must have worked with differential equations, and some of us may still be actively working with them. In elementary education, we are exposed to differential equations which have known analytical solutions or known exact solutions, meaning you can integrate the differential equations using certain integration formulas and you know exactly how to integrate them. But here's the catch, that is not always the case. There are a lot of differential equations which do not have known analytical solutions. There are even a lot of differential equations which have non-existent analytical solutions. Okay, if that sounds too unbelievable, I'll give you an example, and that is this differential equation that looks very simple, but this cannot be integrated, this cannot be solved by analytical methods. Okay, it turns out that most problems in modern research are most differential equations that model physical that actually exist, which do not have known analytical solutions. Okay, and as people in science, it is in our instincts to try to methodically approach solving these differential equations, finding their analytical methods when we don't have any known analytical method. But it turns out that when it comes to differential equations, you cannot exploit any algorithm, any method as such to find the analytical solutions to differential equations with unknown analytical solutions. Okay, so we seem to be stuck deep. How do we come out of this? In short, we compromise. We accept that we cannot find analytical solutions to these differential equations, or we may not be able to find them. And we ask ourselves that can we try to find solutions that are approximately the solutions to these differential equations. And we call them numerical solutions. We try to find them using numerical methods. Okay, the best thing about numerical methods is that they provide you with ready-made algorithms to find the numerical solutions to a differential equation. And we'll have a look at one of the most simple of all numerical methods, and that is the Euler method. Okay, consider any first order differential equation. It is of the following form. By definition, this implies that when the change in your independent variable, that is x here, is so small that it tends to 0, then the change in your dependent variable, that is delta y, with respect to your change in the independent variable is given by this function f. Okay, to get a more intuitive idea, you can try to look at this graph here. So let's say y is your dependent variable. Then for some change in your independent variable, there is a certain change in your dependent variable. And all that we are saying is that dy by dx by definition is the function evaluated at x comma y such that the change in your dependent variable is given by delta x times f. Okay, you can also think of this as drawing a tangent at this point, and dy by dx is given by tan theta. Okay, now all that will approximate here is that delta x is some small value. And as you must be aware that for solving differential equations, we need some conditions. We call them auxiliary conditions. So let our auxiliary condition here be that at a certain value of x, say x naught, we know what is the value of the dependent variable. Let that be y naught. Okay, then we can approximate delta y by delta x at x equals to x naught to be this function evaluated at x naught comma y naught, which basically means that y evaluated at x naught plus delta x is y at x naught, that is y naught, plus the increment in y, that is f times delta x. Okay, this is a very simple method that we use in a lot of situations to model simple cases. Okay, and equipped with this idea of what the Euler method is, we'll try to look at how we can solve the one-dimensional Schrödinger's equation using Euler method. Okay, we define something that we call the Hamiltonian and represent by h cap as follows. This is just a labeling, and this makes the one-dimensional Schrödinger's equation assume a much simpler form. Okay. Then equipped with our condition, it is sufficient for us to have a condition that at time t naught, we know how psi varies with x. Okay. And equipped with this condition, we can approximate psi at x, how it varies with x at time t naught plus delta t to be of the following form. This is very simple to do, and you can use the idea of Euler method to try this at home, derive this at home. It will hardly take you 2 steps, okay? Approximation, right? And it will always be in our best interests to try to improve upon our approximation methods. So is there something that we can do? A very trivial thing to do is that you can keep on making the change in your independent variable smaller and smaller. Okay. Is there something else that we can do as well? We certainly can. We recall that any function can be expressed as a Taylor series as follows. And all that we have been doing so long is we have approximated the left-hand side to be equal to the first 2 terms in the right-hand side. And we call that the first order approximation. But we can also approximate the left-hand side to be the first n plus 1 terms in the right-hand side, and we'll call that the nth order approximation. Okay, and it's very evident that the higher your order of approximation, the better is your approximation. Okay, a very popular nth order numerical method that relies on the Euler method is the nth order Runge-Kutta method. In the upcoming slides, I have modeled the evolution of the wave function with time using the 4th order Runge-Kutta method. Okay, and the first case that we consider is a very simple case. Psi varies with x as a Gaussian function at time t equals to 0 with a certain standard deviation, and the potential energy distribution is 0 everywhere. Okay, so this basically means that the object is free to do whatever it wants without any potential energy barriers or any potential energy maxima, minima, any sort of hindrance. Okay, and let's have a look at how this wave function evolves with time. We see that as we evolve time, this wave function, it sort of spreads out in space. Okay, and as sophisticated and aesthetic that is to look at, let us try something a bit more fun. We have kept the behavior of our wave function at time t equals to 0 the same. We have changed the potential energy distribution here, and it is of the form of a finite well. Okay, classically this is analogous to a particle that is trapped in a box. Okay, and classically we would expect that if the kinetic energy of the particle is less than the potential energy barrier of the box, the particle would not come out of the box. Here, the situation is same, and the kinetic energy of all of the states making up this initial wave function is less than the potential energy barrier. But let's see whether we observe a behavior that is similar to the classical behavior, or do we observe something else? And then we start evolving time. It spreads out in space as expected, and note that as it hits the potential energy barrier, some part of it gets transmitted and some part of it gets reflected. All of the states in the wave function are less than the potential energy barrier. And this is a very peculiar behavior that we observe in quantum mechanics. We call this quantum tunneling. Okay, let's have a look at this again if you want to look at this video. So we start evolving the wave function with time, it spreads out, and then some part of it gets transmitted, some part of it gets reflected, and the part that gets reflected travels back at x equals 0, and then it starts to begin forming a maxima, and we have a maxima at x equals to 0 now. And if I keep on evolving this with time, we'll see that this maxima again spreads out, and then again some part of it gets reflected and some part of it gets transmitted, and so on. Okay. One last thing to end is how do we solve the time-independent Schrödinger's equation, okay? And why is this important? This is important because in nature, we often observe states, the probabilistic information of which does not change with time. For example, consider the molecular orbital of the electron of an isolated atom, okay? None of the probabilistic information associated with the electron changes with time. This is the one-dimensional Schrödinger's equation, and it turns out that the minimum assumption that we need to impose on psi such that none of the probabilistic information associated with psi changes with time is that psi is a product of two functions, one having purely spatial dependence, that is phi here, and the other having purely time dependence, that is alpha here. And note that even though psi is still a function of time, none of the probabilistic information associated with psi will change with time. And it is very easy to show that, but we'll not get into the derivations here. Okay. Under these assumptions, we can do some simple math and we get the following two results. Okay. One is that H phi equals E phi. We call this the time independent Schrödinger's equation. Is that alpha is of that H phi equals E phi. This is an eigenvalue equation, and solving for this gives us bound eigenstates phi n with energies En. Okay, and classically you can consider this analogous to standing waves in a closed cylinder. Okay, and you would see that for a specific case, let's say where the length of the cylinder is fixed, you can have any number of standing waves with a set of nodes in the cylinder states of the wave. Okay, and this is a boundary value problem and not an initial value problem like the ones that we had been looking at earlier. And solving for this is a bit complicated, and we use something called shooting methods to solve for the eigenstates phi n. These are also numerical methods. Okay. The solving practical problems involving differential equations, numerical methods are the way to go. Their use is widespread in various disciplines of science and not just physics. For example, in chemistry, we use them to model the following things, which are essentially almost everything that chemistry comprises of. This animation is of a carbon dioxide molecular orbital. In biology, we use them to model epidemiology, gene expression, diffusion systems, and any number of things. The picture that you see here is something that I modeled a few days back. It shows the expression of mRNA of a certain repressible operon. Okay. Scope of future research is widespread and deep. One of the things that you can do is that, let's say you're working with a certain system, okay, and your system must involve differential equations that have certain specificity to it. For example, are they homogeneous? What is the degree of the differential equation? How many variables does it include, and so on. So one of the things that we can do is we can try to exploit this specificity to develop numerical methods which are faster to compute without compromising the accuracy of our solutions. Something very interesting model on experimental designs. But there are a lot of experimental designs that you cannot build because of physical limitations. But there exist almost no physical limitations in your simulation, right? So what you can try to do is you can build your experimental design in your simulation, which you cannot build physically. And you can try to look at the outcomes and check whether there are any anomalies. And if your theory, if your simulation is correct, and you do find some anomalies, let's say you want to build an experimental design, it will require a lot of funding, a lot of manpower, and a lot of resources, right? So you would want to ensure that whatever experimental design you build, it provides you with the maximum research output. So what we can do is we can try to build those some potential experimental designs in our simulation and try to look at the outcomes to decide which of the experimental designs actually built can provide us with the maximum research output. I would like to thank JBSPDF for providing me with this wonderful opportunity to address all of you here. I must acknowledge my professor, Soumitra Banerjee, at the Department of Physical Sciences, IISER, Kolkata, under whose guidance I learned much of the things that I presented here today. And I would also like to thank my mother and acknowledge her for making me everything that I am today. Thank you.
Thank you, Arkadeep. That was a wonderful talk. So I don't think there are any questions from the audience.
Okay.
So let's move straight to our first reviewer, Dr. Panigrahi, if you will.
Thanks, Arkadeep. It was an excellent talk, particularly given that you are an undergrad. I certainly didn't give any talks when I was an undergrad, so very well done.
Thank you.
I'll say a few things about the talk. So these are most of these are not very, so relatively minor things, and also things that you will automatically pick up as you get more experience. But it would still be worth pointing a few things out. A talk normally has a central argument, right? There's some thesis that you are trying to argue in the talk, and you try to argue it through a sequence of different arguments. So I thought so in this talk, it was a little difficult to find what that central argument was, right? And it only came towards the very end of the talk. So I would encourage you to think of organizing a talk in a way where the central argument that you're trying to push in the talk comes early on in the talk, so that people get thinking about it from the initial parts of the talk, right? So the way the talk was organized, there was a certain sense of the talk being organized in the way that you would maybe write a report or a paper and things like this. But a talk gives you the opportunity of getting people to think sort of in a direct interaction, and it's a good idea to take that opportunity and give people something to think about right at the outset, rather than trying to lay the groundwork initially. And then, of course, once you give people something to think about, you can then step back, try to start laying the groundwork and start making your arguments. So that was one thing. A second thing is, there's always a bit of a challenge when you're giving a talk to a sort of general audience and the talk isn't that long, it's only 20 minutes. There's always a bit of a challenge and tension between trying to make the talk interesting and trying to make it accessible, right? Now, this is a difficult challenge to figure out, even for very experienced speakers. And I think you did a fair job on this. I personally thought maybe the talk just went a bit too slow at the beginning, right? So most of the things that you were talking about in the first 10, 12 minutes of your talk, at least for the first half of your talk, were fairly standard things most people, anyone in science would either be familiar with, or if not familiar, would be able to pick up very quickly. So I would encourage you in such a talk to go a little faster, so that you get to the interesting part of the talk quicker and give yourself a little more time on the interesting part of the talk, right? And that also ties into this question of, are you getting the audience to think, right? So a talk can either be delivered as a sort of didactic lecture, where you stand on a pulpit and give a lecture and you don't expect people to think, people just are getting information from you. But a better way of organizing scientific talks is to try to get your audience to think along with you. And in order to do that, it's important that you sort of throw thoughts and questions and arguments at them that are things that they can think about on their own, rather than just giving them information. Okay, and I felt that could have been done slightly better, in the sense that there were more opportunities for you to take the audience along. So that was the second point. The third point is a talk needs to have some kind of historical context or references, right? So this talk felt a little bit sort of, there was a bit of a sense of, it wasn't clear to me what is 100 years old, what's 20 years old, what's 30 years old, what's current research, what's future research. All of this seemed to be kind of being delivered in the same vein, right? And so it's nice in that if the talk sort of, it's perfectly fine if you're talking about things that are not current research, right? You're talking about things that have already been known for a long time, and you're talking to an audience that maybe doesn't know it, and you're teaching it, right? For example, if you teach in a class, you often mostly teach about things that's already known and have been known for many years. But it's good to make that clear that these are things that are already known, and these are classical things, and this is something that I am positing as a hypothesis that's not known yet. So that distinction is important to make, so that people know which of, otherwise there could be cases where people go away from the talk thinking that all this is kind of new, and these are things that you could think about as researchers, and then realize that all of this has been known for 100 years, right? So, and that can be sort of disheartening. So these are, I would say, the main three things at a high level in terms of my feedback to the talk. And then there was one more thing that's a very specific comment that you made. I just wanted to point that out. So I think on one of the last slides, you used the phrase almost everything that chemistry is about, or almost everything that chemistry comprises. So be a little careful with making such comments, especially about topics that you don't, you are not an expert in and you can't defend. Because the moment you make such a comment, the person who knows chemistry in the audience becomes defensive and takes it upon himself or herself to destroy you at the end of the talk, right? So be very careful about making comments which in some sense are slightly belittling to a person who knows a particular topic, right? So if I were giving a talk, I would just stay clear of these kinds of generic comments. They can hurt you, they don't help you over. Okay. So yeah, so that's all I had. But excellent talk and very well done. Thank you.
Thank you, sir.
Thank you, Dr. Panigrahi. Before moving on to Dr. Bandyopadhyay, there's a question that was posted for your talk, Arkadeep.
Okay.
It is by Arghya Bhattacharya. So Arghya is asking you, what do the videos represent? Can you please reiterate what are the axes? What does evolving a wave function mean?
Okay.
You can access the question in the chat box. Yeah.
Okay, I'll go back to them. Okay, so the x-axis is basically your spatial variable, and the y-axis that you see here is mod psi whole square. So psi is a complex valued function, okay? And what we have, since we cannot plot complex valued functions in a two-dimensional graph, what we do is that we take mod of this wave function and we square it. This also has physical significance, and that was given by Max Born in 1926. Okay, so what he said and what we believe is that mod psi whole square gives you the probability density of finding a particle at with respect to a certain spatial variable. Okay, and what we say when we evolve this with time is that, let's say you have a state at a certain time t equals to t naught, okay? And you would want to look at how the state, the wave function changes with time as you evolve time. This does not happen with bound states we talked about at the end of the presentation. So for example, if I had a bound state here and I evolved it with time, mod psi whole square will stay constant even though time changes. But again, as I pointed out, that if you only plot psi, then psi was still a function of time under the least assumption that we can take, that psi is a product of two functions, one having purely spatial dependence and the other having purely time dependence. Okay, so these are states that evolve with time. These are not bound states. And what we have tried to look at is that how they behave when time changes.
Yeah, thank you, Orko.
You're welcome.
We'll move on to our second reviewer on the panel, Dr. Bandyopadhyay. If you would please.
Thank you very much. Arkadeep, I think it was a very nice presentation, as also the first reviewer said. I enjoyed it. And I've also seen that you have tried to implement some of the presentation techniques that we discussed a couple of weeks back. And it seems to be working, at least for me. I guess that the audience, some of the audience will also agree. Given the fact that you are in your undergraduate, it was a very nicely structured talk, and there are a lot of things that one can appreciate about it. But since we also would like to criticize some of the things that you did and make you a better presenter, I'll start a bit on that side first and then come back to the appreciation towards the end. So I had some comments. So first and foremost, what I felt was that you had a very, very exciting and then title of the talk. You had, when I read the abstract, I was trying to connect with the abstract. As I said also before, that people would have read your abstract and was expecting something out of this talk. So I was looking to understand what is the light at the end of the tunnel. And it's a bit sad that towards the end, I didn't really understand what it was. So what the main message is that you had a nice title, but somehow also, as the first reviewer said, the central message was missing, which often is useful if you start with a general in such a scientific talk, to start with a bit of an outline, to tell a bit about the background, to tell about what has been done before, what is being done, and what is, most importantly, what has been your contribution in this particular presentation. That I felt could have been kind of made out more clear. So that was one of the major points. The second thing that I wanted to touch upon is that it's often good to have some slide numbers on your presentation, because some of us might not remember, and it's much easier to go back to the slide numbers. It's a very minor comment, but can help. And related to that, it was very good that someone asked the question about what these numbers or what this axis means, because I am hoping that there is a very diverse audience here. So taking a bit more time on these nice, interesting figures and explaining the Y and X axis would have been good. But more importantly, what I felt was that something visual before you started explaining the graphs could have been really useful. So for example, you mentioned it that this is like a ball bound in a box or an object bound in a box. Your first slide had a ball in a classical mechanics framework. So I was expecting that a similar object you would put up and say, okay, now I'm going to discuss more about this. So I felt that could have helped. The other thing was also connected more towards the last comment that the first reviewer made, which is about generalizing concepts and also using certain words in your presentation can set some of your non-experts a bit out of context. So for example, in your very first slide, you started saying that if this is something intimidating for you, this is a general way. So it's nice that you're thinking about the audience, but be careful to use the right words, because somebody in the audience might be just thinking, oh, I'm not intimidated. It's a very simple thing that you're explaining, right? So try the usage of words could be something to look at. One more thing, and then after that, I would come back to the parts which I liked of your talk, which is more connected to, once again, I didn't completely understand, is this something of a review that you are presenting? Is there some contribution from your side? Or is there something that you're combining different papers. And that's just because I'm ignorant completely in this field and I'm a more science enthusiast. So some of the things are fundamental and we know, but I was trying to find out where do you have those connections and where you are trying to make your footprint, let's say. I have a couple of technical questions, but I'll come back to them maybe at the end. What I liked is that you were keeping a suspense all throughout the talk. So I was glued to your talk towards the end. So there were some points which we call as cliffhangers, which is like moving from one slide to another slide. There were some points which were quite nice and probably have worked on them. And I guess some of the audience were also thinking or guessing a bit what's coming next. So there was this nice thing all throughout. I actually liked your tempo. And it might be just because of the fact that I like the way you started explaining. So for me, the pace was very nice. But what I missed, as I said, is a clear distinction, what has been done long time back, what you are putting in this field, and what can be expected. So those are mostly my comments. And then I wanted to ask you one question. Since you started explaining numerical methods, I was expecting you would also explain why you used Runge-Kutta fourth order. Maybe that's a technical question on that side, but is there any reason why you chose
I'll
that?
certainly explain that. So the thing is that as you increase your order of approximation, your solutions become more and more accurate, but at the same time, computing them becomes more hectic, it becomes more time consuming, okay? So you need to find a balance between the computation time that you can afford and the accuracy of your solutions that you want. So the fourth order Runge-Kutta method is a very popular method. We also call this the classical Runge-Kutta method. And there's no such reason about, 4 is not a special number. We could have used any order of Runge-Kutta method or any other method that is able to provide numerical solutions in these given scenarios, satisfy the computation time that we can afford, and at the same time, they satisfy our expectations of accuracy.
Absolutely. And I mean, since we also solve a lot of differential equations in our field, I was looking for some numbers over there, what you just now said, accuracy and the time of computation. So a little bit of background before that, before you stepped into why you used Runge-Kutta method fourth order would have been also nice. Yeah, I guess those are all the comments I had. And thank you once again for a very nice presentation.
Thank you.
So once again, I thank Arkadeep and our reviewers. So without any further ado, let's move on to our second speaker of the day. Our second speaker is Mr. Arghya Bhattacharya. Arghya is a third-year Ph.D. student of the Department of Computer Science of Stony Brook University. His interest lies in the intersection of theory and systems, and so he studies algorithms, data structures, and how they improve a system. He did his undergrad in electrical engineering from Jadavpur University and has worked as a research engineer at the National University of Singapore and as a consultant in PwC India before pursuing his doctoral studies. The title of Arghya's talk is How to Write Programs in the Face of Fluctuating Memory. Arghya, whenever you're ready.
Am I audible?
Yeah. Please continue.
Thank you. Arkadeep, great talk. And Mouli, thanks for the kind introduction. I'm also fortunate to have Debmalya and Sulalit in the panel. I hope the box that is coming on my screen, that is only coming on my screen. You can see my entire screen, right? Cool.
Yeah.
So how to write programs in the face of fluctuating memory? Before I start, how many of you have written some programs to solve any problems? or you've ever done some programming. In the interest of time, let me take a guess, maybe 30 or 50% of the audience, maybe not more, maybe more. So is the rest of the 20 minutes going to be a complete waste for the others? Well, no, I don't think so. So you run applications, different applications or programs on your computer. And when you do that, the operating system of the computer, it runs some processes to execute those programs. These processes that the operating system runs, they share a memory. So that is why it is important to understand that why some applications perform poorly. Or in fact, we can call like they have poorer performance than other applications. To understand or discuss about it, let us first understand the model of a computer. I'm going to talk about a model that was proposed in 1988, which is called disk access model. This is pretty popular. What they say is that all the processing of whatever application that you are running that happens in the RAM, we can also call it memory or cache. It has a fixed size of M. Now the data that is required for this application to run, that is not necessarily within the size of M. So where does it stay? That stays in the disk. The model assumes that the disk is of infinite size. Now any data is read or read from the disk to the memory or written to the disk and vice versa. We call this activity memory transfer or IO. This happens in a chunk of size B. Now this DAM model assumes that when a program runs, the bottleneck, the major bottleneck for the running time is the number of IO that this program makes. And this DAM model is very useful to analyze the IO bounds of any programs or applications that we are running. Now, available memory for any program when it runs, it fluctuates over time. Let's say for this example figure here, this figure represents the RAM used or memory used by process 1. Now, as you see, when let's say some process 2 starts and it claims some RAM, the available memory for process 1 reduces. And again, when some process 3, let's say, it finishes, it relieves some RAM and process 1's share of RAM, it increases. Now, memory fluctuations affect performance of a program. As memory gets reduced, the number of IOs, memory available reduces, the number of IOs a program makes, that gets increased. And naturally, the program also slows down, which is bad. Also, there can be another case. When memory increases, the program may not take any advantage, which is also a sad thing. So most programs do not deal well with the memory fluctuations. Now, how do we prove performance guarantees for a program? Before we go further, let us first ask this question, that how do we prove performance guarantees when the memory size is fixed? So for that, we have our old friend DAM model. It is good enough to prove the performance guarantee in terms of IOs for memory being fixed. Now, the next question is, how do I prove performance guarantees for a program when the memory size fluctuates? For that, we need to design and analyze algorithms that adapt to memory fluctuations. So researchers came with algorithms which are cache adaptive or memory adaptive algorithms for that. This research started by Barv and Vidar in 1998. I'm still struggling with this bar. So the only change from the DAM model that happened here is that the memory, they assume that the memory changes at each time step. Memory means the RAM or the cache. So instead of M, you may notice it is now M is a function of time, T. They designed algorithms that adapt to memory fluctuations. We can call them cache adaptive now, these algorithms. They proposed algorithms for sorting, Fourier transform, matrix multiplication, this type of problems. Now, this research was a little bit, paused for a few years. Then there were a couple of papers which said that cache oblivious analysis is very helpful to design cache adaptive algorithms. This research is cache adaptive analysis. It's a generic framework to analyze algorithms. They also found that many cache oblivious algorithms, although not all of them, are cache adaptive. Wait, what are cache oblivious algorithms? So cache oblivious analysis is exactly the same assumptions as DAM model, is another extension of DAM model. It was done in 1999. What they assumed when designing algorithms from this model, the algorithm, they stay blind to the value of M and B. That is the memory and the block size, or at the chunks at which data gets transferred. Now, when we design algorithms like this, we call them cache oblivious algorithms. So basically the cache oblivious algorithms, they are not parameterized by M and B. The journey from cache obliviousness to cache adaptivity proposed by a few theorems. Long story short, cache oblivious algorithms are a very good starting point to achieve cache adaptivity, but there is no theoretical guarantee to achieve adaptivity. In fact, they also proved, these papers at 2014 and 2016, they proved that theoretically there is a logarithmic performance gap between them. So another sad point, because we were about to achieve cache adaptivity with only cache obliviousness, and cache oblivious algorithms design, this is pretty standard, and there have been a lot of research in this. We have a lot of cache oblivious algorithms for some major problems. It was about to get solved, the cache adaptivity problem, but it did not get solved because there is a logarithmic performance gap which was proven. Now the natural question that comes to our mind, that does this gap exist only for certain memory profiles because of some powerful adversary? See, the gap is theoretically proven. So probably the gap, it's a fair question to have, that probably the gap comes from a very powerful adversary, which is not pretty normal, or we don't encounter in real life, maybe. So the question we want to ask is that does it also exist for memory profiles that we typically encounter? So our experimental results that I'm going to show in this work, in this talk, that between two cache oblivious matrix multiplication algorithms, when the memory profile is adversarial, there is a performance gap. But when memory profile is representative of the memory profiles that we typically encounter, we observe no performance gap from our experiments. But before we proceed, why suddenly matrix multiplication? So matrix multiplication, the problem matrix multiplication, it is a representative of a class of problems. And it's a good representative of a recursive class of problems. We also have two cache oblivious algorithms to solve matrix multiplication. One we call MMScan, another we call MMInplace. The important thing is MMInplace is here, cache adaptive, but MMScan, this algorithm is not adaptive. By the way, both of the algorithms are cache oblivious. Now, what these papers at 2016, they proved is that MMScan is a logarithmic factor away from MMInplace. Remember that both the algorithms, MMScan and MMInplace, they are IO optimal in the DAM model. Or in other words, when memory stays fixed, then both the algorithms incurs the same amount of IO, hence the same amount of running time as well. So there must be a worst case memory profile or adversarial memory profile that maximizes the performance gap between these two algorithms. So how do we construct that adversarial memory profile? The idea is that the adversary, or the evil adversary, we may call, this adversary adaptively offers more memory to the non-adaptive algorithm. The non-adaptive algorithm is unable to take advantage of this because it cannot adapt to the extra memory. But the adaptive algorithm takes advantage of it when the algorithm is given more memory. So that's how the performance gap between the adaptive and the non-adaptive algorithm, the gap basically increases. And this memory profile, which is adversarially given or generated, because I'm using the word generated because, as I said, it is adaptively generated. It depends on the state of the algorithm. Basically, the adversary sees what the program is doing, and according to that, it modifies the memory given. So overall, what happens is that MM in place takes advantage of that extra memory given, whereas MM scan is not able to take that advantage. So the results that we find in this research is the following. In theory, we have seen that MM scan is a logarithmic factor away from MM in place. But when we experiment when we see it in the real system, when we observe it with the adversarially constructed memory profile, there is a performance gap that we observe. But when we experiment with the representative memory profiles, the gap disappears. I will talk more about the representative memory profiles in the coming slides. The result is more like the MM scan performs a constant factor to MM in place, within a constant factor to MM in place for representative memory profiles. Let me rephrase the word constant factor here. Basically, the performance gap between these two algorithms, when we increase the input size or the problem size, this performance gap stays around a constant. It does not increase. It does not increase with the input size or the problem size. So it's not a function of the problem size. That's what we can observe from that. And we can call it is within a constant factor to MM in place. Let me reiterate the design space of the memory workloads. One is the adversarial memory profile. We also know this profile as a worst case memory profile. The other one is the representative memory profile, the profiles that we typically encounter in practice. Let me first show the adversarial memory profile, the results with the adversarial memory profile, where we find a performance gap. Even before that, let me show a base case. This is a constant memory profile that I'm going to show you. The y-axis here in the figure is the ratio of I/O of MM in place over MM scan. Let us reiterate once more. MM in place is the algorithm which is both adaptive and oblivious. MM scan is only oblivious but not adaptive. In the x-axis, we increase the problem size. Look at the red plot, which is the relevant one for constant memory profile. The ratio of the I/O incurred by these two algorithms stays around a constant. It is greater than 1, and 1 means they have performed equally. They have incurred the same amount of I/O. Here, MM scan incurs more I/O than MM in place, but that is within a constant factor, not a function of the problem size. So for fixed sized memory, MM scan incurs a constant factor more disk I/O than MM in place. So there is no performance gap that we can expect. Now let us come to the adversarial memory profile. Here the memory profile is generated by an evil adversary. Here the memory profile, the purpose of the memory profile is to maximize the performance gap between these two algorithms. The blue plot shows here that the MM in place, the ratio of MM scan over MM in place, this ratio increases with the problem size. That means MM scan performs progressively worse or increasingly worse than MM in place. And therefore, we observe a performance gap in this case. The plot shows the same thing. It is the ratio of I/O at y-axis, and we increase the problem size here. Now let us discuss that how do we create the memory profiles which are representative of profiles that we typically encounter in practice. In real world, what happens in the real systems when we run programs? Programs share memory with other memory intensive programs. Different users are running programs, different ways processes are running. So basically programs share memory with each other. We run multiple instances, that's why, of memory intensive programs concurrently and let them share a memory. So running multiple instances of a program or copies of the same program simulates the representative memory profile for each of these copies or each of these program instances. What do we find here? Before I go to the result, let me show you what happens with this multi-process performance environment. The plot that I show here is average performance of a single instance when we run up to 4 instances concurrently. And we normalize this to the performance when a single instance is running. The y-axis shows for the 1, 2, and 3, and 4 instances, what are the IU and running time for the instances, normalized to one single instance. So that is why for the 0.1 for x-axis, the value of y-axis is always 1. It goes on increasing as we increase it to 2, 3, and 4. But scan and in place, which are the red and blue ones, you see they stay almost around the same state or almost around the same value. They increase with the same sort of trend when we increase the number of concurrent instances. That means when we increase number of concurrent instances, scan and in place, they are slow down. The amount of slowdown that happens when we increase number of concurrent instances that share the memory, this slowdown is roughly by the same factor or roughly by the same, around the same value they face. Now, let me show you what happens when we run algorithms with representative memory profiles, particularly cache oblivious algorithms. One is adaptive and one is not. We observe that gap goes away. We run up to 4 concurrent instances that share a memory. For all these cases, for all these experiments, the x-axis again shows the problem size. It varies the problem size. Everywhere, the ratio is more than 1. And this ratio is ratio of IO of scan over in place. But scan here performs within a constant factor to in place, which was not happening in the adversarial memory profile. So that means we observe here there is no performance gap within these two algorithms. So before concluding, let us reiterate what we found in this. scan, it cannot adapt to memory fluctuations of the adversary when the memory profile is generated by an evil adversary. And scan is a cache oblivious algorithm. It is not provably cache adaptive, that was shown in that 2016 paper. But scan adapts to the memory profile when the profile represents the memory profiles that we typically observe in practice or in systems. To conclude, cache obliviousness is a great start to achieve cache adaptivity in practice. And also, when we observe the adversarial memory profile, there is a performance gap that is still present between obliviousness and adaptivity. But for the representative memory profiles, the performance gap goes away. And thank you. Here I finish my talk. If you have any questions, feel free to ask. And also, if you want to ask any offline questions, feel free to drop a mail. I also want to acknowledge my collaborators who are from different institutes. Thank you. Thank you for listening.
Thank you, Arghya. Thank you for your talk. We have a question from Smriti. She asks, what you call adversarial today, can it become a representative problem in the future, provided we want more performance day by day? If you could please answer her.
Can I read the question also myself?
Yeah, sure. It's in the chat box.
Okay. Yeah. Oh, because I was presenting. Okay. Oh, yeah. Good question. Thank you for asking. So an adversarial memory profile or adversarially constructing anything, that necessarily means that someone who has more power than you, that someone is kind of observing what you are doing, and what here you means the algorithm is doing. And when you do that, it changes the constraints that you have so that you pay more than that, than what you should or than what you expected. The representative problem is rather, what it represents, it necessarily represents what we generally expect to see in real systems. Now, in real systems, it might be that, in real systems, there are processes which are malicious, which are adversarial. But does it happen always, or does it happen even like commonly? Probably not. And so the adversarial case will definitely maybe be present anywhere, because I can write a program which will be malicious to other programs, and when it shares memory with other programs, the other programs will get affected. But that is not normal. That is not always happening. So should we be concerned for the extreme case always, or we should definitely analyze that what cache obliviousness brings us to, or maybe it's like this work shows that cache obliviousness brings us very closer to achieve cache adaptivity, and we should appreciate that. This is basically the point of this, and what you asked, that is very valid. Did I answer your question? Feel free to ask. Thank you.
Okay, thank you, Arghya. Let's move on to our first reviewer, Dr. Panigrahi.
Yeah, thanks, Argo. Very nice talk. I enjoyed your talk, but just because you are at a different stage of your career, I might sound a little more critical of the talk than for Arkadeep. That's not to mean that I didn't like your talk, but I think you do need some sort of a more critical lens at this point of your career than Arkadeep does. So there are, I'll start up by saying a couple of things, and then I'll try to elaborate on those a bit more. So when you're giving a talk, there are two things that are important to remember. So one is you need to remember who the audience is. And another is you need to remember how long your talk is, right? So in this particular case, you were giving a 20-minute talk to an audience who do not have background, who you cannot expect to have a lot of background in what you're talking about, right? So for a talk so it's a short talk to an audience that's not familiar, right? For such a talk, it's very important to keep focus of your talk on something relatively narrow, in the sense of making sure that one, your audience finds it interesting. Like someone who is just generally interested in science finds it interesting. Someone who didn't know anything about this coming into the talk still finds it interesting. And two, the talk remains accessible to the audience in the sense that you are very frugal with the sort of new concepts, jargon, notation that you introduce. Right? In a 20-minute talk to an audience that's not familiar, you need to be very careful about how many new things you are pushing onto the audience. Okay, so on these two fronts, I felt there was some room for improvement in your talk. So I will elaborate a little more. So as I said, so firstly, any talk, I also mentioned this in Arkadeep's talk, any talk is a compact, is a kind of agreement between the speaker and the listener, right? And what are the terms of that compact? What should the audience get from this talk? What's your central argument? That's something a talk should make a case for at the very beginning, because otherwise your audience doesn't know what is coming, and therefore they don't know what to focus on or what to think about, right? So I think there was a bit of it wasn't entirely clear to me what was your central argument in the talk, right? And that should be very directly and clearly and easily presented at the beginning without any jargon. It should be presented in a way that everyone gets hooked onto the talk. and doesn't lose you in the middle, right? So it's important that a talk starts off with that central agreement. Like it's like a handshake. Look, you have come to my talk, you are spending your valuable time sitting and listening to me. This is what you are going to get out of it. Okay, and that again wasn't very clearly described at the beginning of the talk. And generally, I felt that there was just too much going on in the talk. There was too much going on in the talk. There was too much going on the slides, and I'll give one or two examples. So for someone who doesn't have knowledge of these things, there is a very good chance that you could have lost that part of the audience in this talk. So a few things that could be improved. So as I said, think of whether every piece of notation is required. So you're talking about this, for example, I saw somewhere that you use I think you used M for maybe memory, B for the disk, or the other way around, something like that. And that notation just vanished after that. You didn't need that notation. Okay, so you use this thing about log versus constant. Again, not required, right? All you needed to say was that there is a gap there's a difference between what you observed for worst case instances and what you observed for typical instances. Because you have to, and I'm saying this because if you are giving this talk to an audience that knows computer science, then you can say log and constant and people know what you're talking about. But for an audience that's not familiar, you're just introducing unnecessary things, right? That's not the central message of the talk. You went into this thing about like matrix multiplication, why is it representative and so on. Again, not really required. You could just say, this is one example, and then say a couple of words about, is this phenomenon more generally true? You could say that we need to do more experiments to figure that out, or you could say that this is why we believe it should be more generally true. But again, details weren't required about what that meant. You also talked about adversarial versus representative. Again, not required. All you needed to say was without using the jargon, you could have said things about how usually in computer science, we talk about whatever is the worst possible input for your algorithm versus what we care about in practice often is what is the typical input for your algorithm. Okay, so try to, in a talk like this, you must try to keep the jargon down to the maximum extent possible, right? Because every bit of jargon that you're introducing, you risk losing the audience. I also felt that the talk was slightly weaker on the broader context. So it just went, it wasn't, so normally the way most successful talks are structured is that it has a sort of very focused flashlight on a particular thing that you are on a particular, as I said, the compact of the talk or the main central argument of the talk. But then you also step back and make a broader point around that specific thing that you wanted to convey in the talk. In this case, it almost felt like I was waiting for that broader point to come and it never did. Okay, so for example, you have observed this difference, so what? And that so what wasn't clear in the talk. Okay, because the way I would have structured this talk, I would have gone very directly. I would have talked about, look, in any computer algorithm or computer system, there is some memory and it processes data in this memory. Now the available memory keeps changing for whatever reason. You didn't again need to go into OS and so on. Just say the available memory keeps changing over time. So here is a thesis that people have suggested in terms of how to adapt to this changing time. And then you could have gone directly into, this is what my experiments are saying. Okay, so it needed to be a bit more direct. I think there was just too much like superfluous stuff going on, and it did feel a little bit as if you had a sort of 1 hour talk and you somehow compressed it to 20 minutes rather than you designed a talk for 20 minutes. Okay. And in the process of introducing all this additional jargon, what happened is the things that you did really need to introduce carefully didn't get the time it deserved. For example, your entire talk was about these two concepts of cache obliviousness and cache adaptivity. And I felt that particular, for example, I didn't quite see where cache obliviousness was described properly in the talk. Right, so all these extraneous things seem to dominate, and the main central two terms that you really needed to describe, because that's what your talk was about, those terms didn't get the attention they deserved. So I would generally say that in a talk like this, as a sort of interesting research talk, to make it an interesting research talk, it's important to say what your message, like say clearly what your message is, describe the main describe the limited amount of jargon that you need in order to convey your message, the minimum amount of jargon you need to convey your message, but describe the central aspects of the talk, the central concepts that the talk is focused on, describe those in more sort of with more care, and then look forward a little bit. So in the sense that, okay, so this is something I've observed, so what next, right? And why should you care about what this observation that I have made? So that broader context, focus on the use of sort of terminology, make that as limited as possible, and focus on the central message rather than talking about all these different things. And also just one last thing, something specific. So as I mentioned earlier, that there was too much happening on the slides, and I think a lot of those were not necessary. So for example, if you went back to your slide about disk and memory, so these, yeah. So
you mean the
fast
figure?
Yeah, for example, yeah. And so, I mean, for example, what are these boats moving, right? So this is kind of extraneous stuff, right? And if you are, I know that there is this tendency for us to kind of make this cool, right? That I have like boats moving from one sort of island to the other. But in order to make, the fact is that you, of course, you in the talk, you don't have enough time to say like these are actually boats moving with data from one to another, right? So by introducing this, these images that are kind of don't convey, like just trying to make the slide look cool, you are risking people getting confused about whether this is something actually important that they don't understand, right? So I would say, like, keep your imagery as limited as possible so that people are not kind of distracted by these additional things that are not important to the talk. Yeah, that's all. Yeah, and thanks again. Thanks for the talk. Yeah, overall, I did like the talk.
Thank you. Thanks for your feedback also. Yeah.
Thank you, Dr. Panigrahi, for your input. Moving on to our second reviewer, Dr. Bandyopadhyay.
Thank you for a very nice talk. I think I agree with most of the things what the first reviewer said, but I have some additional things to comment on. So first and foremost, again, the purpose of being a bit more critical with you is also that you are in your PhD phase where you are more, let's say, expected by the research society to make a landmark presentation more than Arkadeep, right? So he has still in his undergraduate. But there are a few things. The first and foremost important, what I felt is that you started with a very nice question. I like the question, and I thought, okay, then I am in, because I'm a generalist in this talk. And I was looking for following it all throughout, what has been done and what your results show. But what I missed out is that I did not get a clear overview of what's in it for me. Although you tried to glue me in the very beginning, you said that even if you have not written programs, this is not a waste of time. And I thought, okay, that's very nice. But I slowly lost you towards the end of the presentation. Now, there are different ways of keeping an audience attracted to a talk, even if you are not you will not be able to gather your whole audience for all the time of the talk, unless it's absolutely memorable, which we all are trying to aim now. So one good thing that you could have done is had a very clear outline, and you could have shown a bit of the progression. Where in your talk are you right now? So some of us who are probably not going to look into your results too much detail, but want to know what is the outcome of it, could have probably, let it a bit loose, because there was too much things going on. There were too many distractions. So these boards, for example, as you now have, I recommend that there were several slides where you, for example, your legend on the right side was bigger than your main figure. So at some point I thought that I should focus on the terms, which is MM in place and MM scan, rather than looking at how the red line or the blue line is going and what it means, right? So those I felt was unnecessary. And what I strongly felt all throughout is that it's very easy in a digital platform now that your slides are popping up right in front of your screen. So you are using the slides too much than using what you have prepared for, if you get my point. So the slides are basically an aid for you to present, but your focus was mostly on the slides. Where also, then I would have liked you to probably pop up different things on the slides as a small animation to show, okay, now I'm focusing on the main graph. So here it is. And then a one-liner which comes later. So that could have helped. There was too much things on the slide. And honestly, many of us didn't know where to look at. Coming to the title, again, what I mentioned, that you also had an interesting title, but you never explained to me what that title is. So as I now see that you could have structured the talk into two parts practically, and you could have explained, for example, what you're meaning by, let's say, writing programs and all that part into one block. And then what you are trying to do with your work is probably tackle the fluctuating memory part of it. So there was a missing link, because remember, we have come to listen to you based on your title and based on your abstract, right? So that's why we are here. So you should do justice to that title. Slide numbers, again, it's useful because now also when you wanted to go back, it would have been easier for any person to say, okay, go to slide number 13. It's a tool, use it, it helps. I felt also that your talk was not tailored to this audience, which was also a point from the first reviewer, that you probably had this presentation for a specialist group, and you took out some slides and added some things for this presentation, but give time to each presentation, since all the audience is actually giving time to listen to you. So even if you are spending, let's say, 2 hours for preparing a 20-minute talk, 30 people listening is spending 20 minutes. So you can calculate that it's a lot of time that people are listening to you. So spend more time. That's what I felt. Another thing I felt is that, in such a presentation, you have 4 important things that you cover. You talked about the context very nicely. You talked about what people have done. That was very good. But then you started showing your results. And what I failed to understand is that, is this something new? Because I'm not an expert in the field. So I'm trying to think, is this something absolutely new, novel, or is this something, let's say, a little bit of a tweak in other people's work or in the literature? So what part was missing in your talk is, if you would have been clear, what have people not done in this field? And therefore, why is your contribution so important, right? So that part was missing in that whole puzzle. And the last thing that I would like to speak about is mostly on like the time that you took, which also the first reviewer mentioned. So I felt that you explained some of the concepts which were not so necessary for your final message. And you actually did not do justice to the actual content of your talk, where you kind of hurried through. I mean, it was a nice tempo, but you skipped some of these important terms that you use, and the jargon, which was also a similar comment. I guess, having said all those, I think what I also enjoyed is that you had good control of the talk. So you knew what you're talking about. It's not that that was lacking. So the audience could start to build in confidence in what you're showing and trust in your results. But 20 minutes is too short, right? So if it was a 45-minute talk, towards the end, we would have had an excellent impression about your knowledge of the subject. But in a 20-minute talk is more to just come out with the central message and stick to it. So thank you once again.
Thank you. Thank you for the comments. Yeah, these are very helpful.
Once again, I take this opportunity to thank our speakers and our reviewers. Thank you so much for accepting this invitation and for making the first event happen successfully. We've come to an end, so thank you once again.